I'm Callie Hunt. I'm a biomass research engineer at the NRRI, or Natural Resources Research Institute. And today I'm going to be talking about NRI's metallurgical biocarbon research program, specifically focusing on the EAF steel mills. I'm going to give you a little background on NRI if you guys don't know. The NRI was established by the Minnesota State Legislature in 1983. We have three major research platforms: the Future Forest Industries, Iron and Minerals of the Future, and Ecosystem Resilience. And we really work collaboratively on a lot of projects, so most of our projects teams are interdisciplinary, and you'll see here how our groups work between the Future Forest Industries and the Iron and Minerals of the Future, specifically on this work. NRI is part of the University of Minnesota Research Enterprise. We bridge the gap between academic and integrated research solutions. We really focus on translational and applied research. So first I'll give you an overview of our biocarbon reductants program. This is a pie chart from 2016 of the global greenhouse gas emissions. Up at the top you can see that, where's the pointer? See up here, iron and steel accounts for 7 to 8% of the global greenhouse gas emissions. And NRI has expertise in both metallurgy and biocarbon production and characterization. And so we kind of started to play around with the idea, can we engineer a carbon neutral fossil carbon replacement? And so our concept, where are we at? Sorry. Okay. I changed some of my animation, so I got thrown off a little bit, but we'll go forward with this one. So our concept was to demonstrate a carbon neutral engineered biocarbon product to replace fossil carbon in the EAF steel production. And what impact would this type of work have? In 2023, over 100 million tons of steel were produced, and 70% of this is via the EAF steel mills. And our goal was to create a fossil carbon replacement that had no reduction in performance or steel quality. And the project sponsor for this project was the US Department of Energy, totaling about $4.5 million. Okay. I don't know if this just died or what, but I'll go. We're frozen. It's stuck. Holding. I'm even trying on the computer. It's not doing anything. It appears as though I could try to exit out and see if this does anything. Let's try this.
Well stuck. Let's restart.
So many animations on your presentation here. There you go. Okay. All right. Does it go forward from here? Nope. Just want to focus right on this slide. I don't know if I have any more to say specifically on this one.
Let me jump ahead to the next slide and see if we can start there.
Here we go. If we can just go to that guy.
There.
This one up. There you go. All right. A carbon source is required for the metal oxide reduction. So some of you might be wondering, like, why are we using carbon in the steel industry? So to get from iron oxide to just iron reduced, we need heat, and then we need a carbon source. And so right now, the industry is mainly using fossil carbons, and then of course CO2 is an output from there. And then NRI is getting into other metallurgical places, but this specific presentation is going to focus on the reduction of iron oxide. So where is carbon used in the EAF? Sorry for those who already know this answer, but I'm going to talk about charged carbon. So charged carbon goes in with the iron materials into the molten iron, and then also it's injected as injection carbon to promote slag foaming. So those are the two spots in the EAF process, and then there's the graphite electrodes that produce the heat that melt the metal down. So injection carbon acts as a baking soda to help the slag layer foam. You can see the reactions here. What are the benefits of slag foaming? So one, it helps protect the refractory electrodes. It helps with metal bath insulation. It also helps with impurity removal. So we're helping remove the sulfur and phosphorus and other things that we don't want in the end iron. And then it also helps with noise insulation. And then this is a little image of, you can see they're injecting the carbon into the slag layer, and then that produces bubbles of gas, and then that from there creates the slag layer to increase. So the scope of work on this project, we focused in phase 1 on injection carbon at the lab scale, then we plan to move into charged carbon at the lab scale, and then phase 3 we plan to do 20-ton pilot plant production trials with a commercial partner. So as you can imagine, there are a lot of challenges that we encountered when looking at a biocarbon replacement. First off, feedstock variability. Any biomass stream is going to create a different type of biochar, and so we had to play around with lots of different feedstocks to get the geometry and substructure and volatiles content, ash content that we wanted. We also knew that we needed a high fixed carbon, so we needed to go from about 50% fixed carbon to greater than 80, which requires a high pyrolysis temperature. We also know that it needed to be dense. Regular biochar does not interact well in the EAF environment. It just kind of floats on top, or if it's too light, it just flies off with the flue gas, so it's not going to interact if it's not dense. Also with porosity, if it's too porous, which in some cases you want a porous biochar, in this case it turns out to be too reactive, and so we had to figure out how to control the porosity, leading into densification. So we ended up densifying our formulations at those high pyrolysis temperatures. We can't actually densify without adding additives back in. So that natural lubricant or lignin that's in wood or other biomass for pelletizing or densification is no longer there after pyrolysis. So we needed to figure out a way for it to stick together. And then also we needed a way to validate these formulations at the lab scale. Right now, there's no actual standard test that exists to know, like, how is this going to perform in an EAF? We wanted to know that these formulations would work before we went up to the 10 to 20 ton trials. So next, I'll move into our methods. Where are we at with time with that pause? Okay, we're doing okay. We're going to talk about our pyrolysis, densification, and then our metallurgical tests. So for pyrolysis, I think most of us know here, we took biomass feedstock, pyrolyzed it, and then came out with a biocarbon product. We played around with a lot of feedstock, particle size, resonance time. I think many of you know who produce biochar. Making the biochar is not the hard part. It's dealing with the syngas that is actually the hard part. So we have a lot of learnings there as well. Then into densification, we took the biocarbon, we milled it down. See, my video is not playing. Okay. Well, you're supposed to see a video in this extruder here. It comes out looking what we call carbon spaghetti, so it's kind of shooting. We had a cool video. I hope my other videos work, because otherwise that's going to be a problem, but we'll figure that out when we get there. And then we get this densified pelletized material. And again, this is for the injection carbon. One of our metallurgical tests that we did was a modified coke reactivity index. So we basically take the carbon sample and then measure the weight loss over time in a high temperature environment. And then a high CRI means it's very reactive. So here you can see, I have a graph here. Where are we? Here we go. So the weight remaining is on the y-axis, and then time in minutes is on the x-axis. And so unmodified, just biochar as is, was the most reactive, and the coal products at the top were the least reactive. We threw in some activated fossil carbons just to get a representation, and then extruded or densified material, you can see how much we improved or decreased the reactivity. And so what we learned is that biocarbon is more reactive than fossil coal, and porosity does correlate with the CRI. So you can see here, this is the SEM image of the fossil coal. This is the pre-densified biocarbon that still has that structure, all the pores, and then our densified material on the far right. And you can see how it's a lot more comparable to the fossil coal. We also developed an in-house procedure for slag foaming. We can actually measure the slag height over time, and then we also sampled the slag and the molten steel before and after we added the carbon.
What is the binder?
We played around with a couple different ones, but they are natural binders. We can talk more on the side, but yeah, we play around with mostly natural binders that are available commercially too, so it's not some secret binder that we have in our lab. It's commercially available. So moving into results, we played around with a range of pyrolysis temperatures, which then would give you a range of fixed carbon percentages. We played around with feedstock species, high and low volatile content, our ash chemistry being acidic and basic, and then we also added performance enhancing additives. NRRI has intellectual property related to EAF biocarbon formulations. We also have a team that does a lot of biochar characterization. I'm going to highlight our surface morphology and pore size work, but if you're interested in any of that, come check us out. We got a lot more than what I'm talking about today. But we already saw these SEM images, so this is just injection carbon used in the industry. This is our biochar before densification, and then our biocarbon after densification. Again, some images to correlate. And then this is a pore size distribution. We have a kind of a unique pore size distribution. This is on the logarithmic scale, so there's a large range of pore size here, and then the log differential of the pore volume on the y-axis. In black is anthracite coke. You can see it has a relatively small pore size distribution. The green line is our biochar before densification, and then you can see the red line is the biochar after densification. So this really brought it down and closer into the range of anthracite. We also had some density and durability requirements from our industry partner, which they gave us. It needs to be at least greater than 27 pounds per cubic foot. In black here we have, I'm surprised our units on my graphs are not here. Sorry, there must have been some weird conversion with my presentation. But so the black is anthracite, and then the rest of all our formulations. All of them surpass 27 pounds per cubic foot, and then some of them are getting close to that anthracite density. We also did tumbling durability. We needed to be greater than or equal to anthracite, and all of our samples actually exceeded that there with our tumbling durability tests. And now the sad part, my videos are not gonna be able to play. I don't think they're gonna. Oh, maybe. Okay. All right. So when I play them, this is a video of our slag foaming test. So one sample is going to perform really well. You're going to see it foam. The other sample, it's going to not react at all. And so this really showed us that the formulation does matter. All those parameters that we played around with make a difference. And so you can't just throw any biocarbon biochar in for an injection carbon and have it work. Oh, okay. If we have time, I have a thumb drive, so maybe I can pull it up. I don't know. Let's see. It's not even showing a video on here. So, okay. I'll try to go fast, and then maybe I can pull my thumb drive up, because this is the coolest part of the presentation. Just a big bummer. So we can correlate, basically we collect that slag height over time as well. So in the video there's one that performs well, one that doesn't, which correlates to this line. So this foam height grows over time. So we have the slag height on the y-axis, time on the x-axis, and it grows. And then this one, it just kind of hung out and didn't really move that much. So then we have anthracite here in this red line. So it has a different curve. This one's a little bit more of a sustained foaming height, but it doesn't get as high as anthracite. And then we have a lot of other formulations that we did. This orange line here exceeded the slag foaming height of anthracite. We had some other ones that failed. This black line is similar. So we're seeing promising results with our pyrometallurgical tests. Again, we need industrial trials to prove that these bench to lab scale metallurgical tests actually correlate to what we'd see in industry, but this is promising. So scale up, again, we need to do these commercial scale trials to validate what we're doing now. It also let us know, does it convey well in the systems that they have? Is it compatible with the pneumatic injector, the foaming performance? And we really need to correlate what we're learning in the lab to what we can do in the commercial scale. Again, I'd like to acknowledge the US Department of Energy, and then this would not have been possible without our project teammates Nucor and McCovery. I was gonna open up to questions, but I'm gonna try to grab my thumb drive quick and see if we can get this video. Okay. So we try to keep everything the same. It took a long time to create this test. We played around with a lot of different parameters. And you can see the one on the left here is starting to foam. You can see the bubbly slag layer, and the one on the right is not reacting really at all. You can see even the pellet shape is not even changing. Am I blocking anybody? Okay. We also did like a carbon balance, so like we kept everything the same that we could in these tests so that we get reliable and quality data. And I don't know if you saw the little blip. We fast forwarded, otherwise you'd be sitting here for 9 minutes watching the whole test. So, yeah.
What month of the year?
What month of the year? This was done in like February, this past February.
Unfortunately, economics eventually worked their way into the equation. What is either the current price of pet coke that they're using that you're trying to displace, and if you have any thought about what you can make this at a commercial scale, that would be a great ratio to know about.
Yeah, I don't have the numbers off the top of my head. We did do a TA and LCA as part of this work, but it was very preliminary because we only had like our lab scale work. So our TA and LCA are supposed to improve with each phase of the project. I'm trying to remember, you have the number off the top of your head? 300 dollars per ton? $300 per ton?
That's pet coke now?
Yeah, that's metallurgical coke.
That's what you're trying to replace?
Yeah.
Yeah, and we'll say we're within range.
Yeah, no, you are close.
Yep.
And does the steel producer get any credit or reduction credits?
In Europe and other countries, they do, and much like a lot of industries, they're paying a carbon credit or a carbon tax or whatever, and less so in the U.S. Although it depends on their end users, the markets. If it's the auto industry or something, if there's a global. They're playing in the global market, it will matter more to them.
Mm-hmm. And the thought is like, the trees or whatever biomass are taking in CO2 at the end of their life, we're turning into the biocarbon and then is used as the metallurgical carbon. So we're not necessarily eliminating the CO2 emissions, but it's a carbon neutral alternative. If that makes sense? Yeah, correct. Yeah,
Yep.
Yeah.
Yeah, is there anything that could be put into any of the federal lobbying going on now that could be useful, helpful
Yeah,
down the road? Or?
our director of research is currently working with lobbyists. It's helpful. We've changed the way we describe it as being like globally competitive in the steel industry instead of like decarbonizing the steel industry. So, the way you talk about your projects can change so that we can still maybe retain funding. So that's kind of, but yeah, any lobbying is great, and especially getting federal funding. So we're kind of, specifically with the funding source, we have, yeah, it hasn't been taken away, so our hope was to be able to keep going. Our just continuation application has just not been reviewed yet. So we really don't know where that's going, but we do have a lot of industry support, so we're kind of trying to open up those avenues and continue the research in other ways. But yeah, our hope was to take our learnings from injection carbon, move into charged carbon, and then do commercial trials.
But we're actively seeking industry.
We are,
partners.
yeah. Actively seeking industry partners. Come find us at booth 604, or have our cards are available to come grab. Yeah, this is Eric Singsauce. He's our program research leader and at NRRI.
Yep.
Do you have another idea, different than this one, but with the same notion that biochar or something could have another?
Yeah, so we really want to get into the other metallurgical options. So there's like lead smelting and silicon and all sorts of other, I mean, I'm blanking on the other one that we were just talking about today. But yeah, just basically taking these learnings, we know that you can't just throw anything in there. So we have the expertise to kind of analyze the carbon that they currently are using and try to come up with a biocarbon that has those same properties. Oh, you're up here.
So Michael Antel years ago had a process called flash carbonization.
Okay.
It was a pressurized process that made much higher yields because it basically left a lot more carbon atoms in the char. It was basically the best fuel char you could make. It was about the worst biochar you could possibly make. And a company called, I think, Carboculture has taken that reactor design forward. So, there may be some interest at the laboratory scale of creating specialty carbons with much higher secondary char depositions, because that's really what you're doing with that whole binding thing, is trying to plug some holes to get the CRI down. So it's just, I don't know if your budgets expand out that far. That's a little bit University of Mars stuff, but it is in the literature, and you might not overlook it, because a better starting point is a better ending point.
Yeah. Thank you for that.
Yeah, thanks.
Any other questions?
All right, well, thank you guys very much.
Thank you.